Thank you very much for the kind introduction. And first of all, I'm sorry to not being able to be here with you physically. I have some connectivity problems, so what you're seeing right now is a pre-recorded talk. I will try to be with you in the session and to answer questions after the talk. Yeah, that's just the way it is. So, after all these very interesting and fancy materials which have been introduced in the preceding talks, I would like to introduce yet another material system for you today. And these material systems are so-called transition metal dichalcogenides, which are a class of monolayer system. I will specifically looking into a pathway towards optical applications for these materials. So my name is Falk Eilenberger. I'm from the University of Jena, but most of the work has been done by my colleague who is the first author of this talk. So transition metal dichalcogenides are, or specifically monolayer transition metal dichalcogenides are monomolecular two-dimensional crystals where you have one sulfur and selenium atom at the top layer, another at the bottom layer, and then a middle layer where there's a molybdenum or tungsten semi-metal. These materials are direct semiconductors, yeah. And as a bulk material, we have multiple of these layers stacked on top of each other. These are indirect semiconductors, so therefore for optical applications not so interesting. But as monolayers, they become direct semiconductors, and that's of course very, very interesting for optical applications because direct semiconductors have very, very strong light-matter interaction. And you can see this here again on the left-hand side, where you see the band structure of the bulk, indirect, and of the monolayer, direct. Yeah, and one of the consequences of these, or one of the emerging properties which you have due to this transition from indirect to direct semiconductors, is that as monolayers, these have very, very strong photoluminescence. So you see here in the center of the slide, you see the photoluminescence spectrum, and you see it's the double layer. Photoluminescence is very, very dim, almost no photoluminescence, but the monolayer has very strong photoluminescence, which is resonant at a specific wavelength roundabout at the red end of the visible spectrum. And this photoluminescence is mediated by excitons, which are like bound states of holes and electrons. Yeah? And these have one peculiarity in 2D materials, namely that a large part of their electrical field lines actually stick out of the 2D material, and this makes these photoluminescence features all very, very sensitive to the environment. So the take-home message, yeah, and these materials transition from indirect to direct semiconductors as a monolayer. They have very strong photoluminescence, and this photoluminescence is driven by electron-hole pairs. Now, this is not the only interesting properties which their materials have. They have a lot of interesting properties in optics and photonics. And during this talk, I will also look into a second property, namely that is their strong nonlinearity. So these materials are highly nonlinear, which means that they can, for example, convert two photons into one photon of higher energy, which is called second harmonic. And this is something which is frequently used in light converters or quantum light sources. However, before you can make these, if you can use these interesting features and effects and turn them into applications, you first of all have to master fabrication and integration into optical system with these 2D materials. The state-of-the-art method to produce these materials, or one of the state-of-the-art methods to produce materials, is so-called a chemical vapor deposition, where you basically bring together precursor materials for the transition metal and for the chalcogenide in a hot reactor, and then you can, under the right conditions, grow crystalline monolayer films on substrates. So what you can see in the bottom here are two pictures from a collaborator which grow these 2D materials for us. And what you see on the left-hand side are monolayer crystals of MOS2. The size is about 50 nanometers, and on the right-hand side you can see a so-called heterostructure that's basically a single monolayer crystal, yeah, where you have molybdenum selenide in the center and tungsten selenide at the edge, and the connection between the two is basically epitaxially solid. Yeah? Now, these materials are so-called van der Waals materials, which means that out of plane, they are just bonded to the substrate very, very weakly. And this has a few interesting consequences for growth, namely that they grow on almost all materials in a crystalline manner, even on amorphous substrates, yeah? And they also grow in almost all structures in a conformal manner. So you're not bound to grow them on planar structures, you can even grow them on curved substrates. For example, this is very, very interesting for direct and scalable integration with photonic circuits. And the simplest photonic circuit is, of course, an optical fiber. So what we did is we used a special kind of optical fiber, a so-called exposed core fiber, and grew these 2D materials with this CVD process directly on the optical fiber. So the fiber is displayed here on the left. Yeah, what you can see here is a cross section. Yeah, and the light gray area is silicon dioxide, and the dark gray area is air. Now the important stuff happens in the central region here, yeah, which is zoomed in at the top left for you. So you have a suspended core of silicon dioxide. This is where your light propagates in a mode which is surrounded by air. And if you place these in a CVD reactor, the top surface is exposed to the outside world, and you can actually get in contact with these material vapors, and you can grow 2D materials directly on that surface here. Now the result of such a growth, yeah, is shown on the right hand side here, and you see these nice monolayer crystals which are growing directly on the optical fiber. So this is an ordinary microscope image of such a fiber. Now after you've done the growth, yeah, you first of all we need to make sure that this material is of sufficiently good quality and that we actually have grown monolayers. So you can do AFM or Raman scans. Yeah, and the important part is that from these triangular crystals here, yeah, you can measure a height of 0.7 nanometers, which is just what you would expect for such a monolayer. And we measure a separation of the two characteristic Raman peaks of 20.5 per centimeter, which is also a signature for monolayers. So with this, we know that we have conformally grown on the curved substrate of our fiber, and that this growth really contains monolayers. So in the next step, you can look for photoluminescence, which is not just a signature for monolayer formation, but also a signature for good electronic quality. Yeah? And you can see the fiber core here, yeah? And you see that in this fiber core we have these nice triangles which have grown on them and which have very, very strong photoluminescence. And then if you measure the photoluminescence spectrum from any of these, you will get this typical spectrum which you see here, which is just what you would expect for CVD-Grown MOS2. Yeah, so long story short, the electronic quality of these 2D materials is really good. And now that you have done this, you can kind of proceed and really make fiber-based experiments with these 2D materials. Fiber-based experiments, very simple. Yeah, you have your light source on the left-hand side. You propagate light into the in the guided mode of the fiber. The light propagates down the fiber, and as it does so, it interacts with the 2D material crystals. Yeah, they will emit some light sideways, which you can image from the side, but most of the light will actually go into the fiber core, and this is something which you can then record on the right-hand part of the setup using cameras and spectrometers. Okay, that's what the setup looks in reality. So this is our fiber here in the center, which is a few centimeters long typically, but can also be shorter. You can just cleave it to shorter pieces if you need. So first of all, we'll just do the sideways mapping which is really helpful because with the sideways mapping, you can just illuminate from one side and then you see all the crystals which are in contact with the core light up and start emitting photoluminescence. And then you can just scan your camera along the fiber to map the location of all the monolayer crystals. So for this specific fiber, you find 39 distinct locations of monolayer crystals with a total length of 1 millimeter, which is a coverage of 5%. The typical spectrum looks like is shown here, and which is again what you would expect from a monolayer grown on a planar substrate. So the total length here is 1 millimeter, which is, keep in mind, it's an interaction length that you now have available, which is 6 orders of magnitudes longer, as opposed to when you just have one monolayer crystal and you look through the monolayer crystal. Yeah, so this is a massive enhancement. It's a whole different ballgame. Okay, now we forget the sideways observation. We now take the fiber and then we look through the fiber. So at the exit port of the fiber, you typically see something like this. Yeah, so this is the photoluminescence light, which is leaving the fiber where the excitation laser is blocked off by an optical filter. You can route this into spectrometer, and again, you get your typical spectra for MOS2, and in this case here I've also plotted a spectrum for you with WSE2, which has a slightly different central wavelength. So what we've done here now is we've basically both excited and collected the photoluminescence emission from our 2D materials through an optical fiber. Now you can immediately use this for optical sensing. You just take your fiber as it is, yeah, and below NH3 over the fiber, which is down here. Yeah? Sorry for the quality of the graph that just came out of the lab 2 or 3 days ago. Yeah? So this is the photoluminescence intensity on this axis. Yeah? And at t equals 0, we have blown NH3 over the fiber. And you immediately see that the photoluminescence drops until after minute 60, we start to purge the fiber with NH2. So what this shows really is that these fibers are suitable for remote sensing and that they're very sensitive. However, what you always need to keep in mind, this is sometimes an issue of selectivity. Yeah? So this is an early example. Now let's change gears somewhat and let's exchange the CW excitation for pulsed high power excitation. Let's go looking for nonlinearity. We'll be looking at 2 effects. First, third harmonic generation, and then second harmonic generation. So what you see on the left hand here is basically curves of third harmonic spectrum, which were excited by a laser at 1590 nanometers. Yeah? And what you see are superimposed the spectra which come out from a bare fiber without a coating and the coated fiber. And what you see consistently is that there is more third harmonic coming out of these fibers if the 2D material layer is present. What you also see if you take more data points, that this behavior is kind of like cubic, yeah? It's just what you expect for for third harmonic generation. Now, describing the entire process in detail is rather complicated because there is no phase matching at the fundamental wavelength, only at a wavelength which is slightly shifted and it's phase matched to higher order modes, and it's pretty much a nightmare. Yeah? But long story short, it turns out you can model this behavior, at least qualitatively, and you can see that just a single monolayer, which covers 5% of the fiber length, is sufficient to significantly alter the nonlinear behavior of these optical fibers. And this is something which I find quite amazing. So what we then did, we again changed the laser now to an excitation wavelength of 800 nanometer and tried to excite second harmonic. This is actually much nicer because the fiber in and by itself has extremely little second harmonic, because silica glass has no second harmonic, and this fiber only has a little bit of second harmonic due to the surface nonlinearity of the glass-air interface. Now again, we recorded the spectra of the second harmonic, yeah, And I'll just keep this brief. What you can see here is that these solid lines, which are the bare fiber lines, and that have already been amplified 50 times so that you can see them at all, are much, much lower than the curves for molybdenum sulfide in this case. So all in all, with this fiber, we have achieved a more than 1,000-fold enhancement of second harmonic generation. And what's particularly noteworthy is that we find this slope of 2 in the center with very, very high precision. Yeah? But what we also find is that there's actually more second harmonic coming out of shorter fiber pieces as opposed to longer fiber pieces. And this is related to the fact that these fibers start to become quite lossy if there is too much 2D material on the fiber core. Moreover, our second harmonic process is not phase matched yet. Yeah? Keep in mind the discussion which I just made with you with third harmonic generation. So what we believe is if we can make these phase matched, and we have a few ideas on how we can do this, we should get another 3 or 4 orders of magnitude enhancement from the second harmonic process, and then this would really be interesting for applications in optics and photonics. So to summarize, what I've tried to convince you of today is that if we grow monolayers directly on optical fibers, then that we can use this as a platform for integrated experiments and applications with these 2D materials. I've shown you that we can interrogate these monolayer properties through optical fibers by demonstrating enhanced third harmonic generation, really, really strong second harmonic generation, and remote sensing of NH3. And I'm quite confident that there's going to be much more experiments to follow in this fiber optical, let's say, hybrid fiber optical systems. So thank you very much for your attention, and I'm happy to take questions.